that the audience can see the full screen. Could you relocate the chairs to either side? No, I mean, those chairs are around the screen. You don't have to do that. Thank you, everyone. Thank you, Gregory. All right, let's get started. So we have, this is the last session of the day, and we are at the session 6B. The theme is novel sensing. So before we get started, let me just briefly introduce myself. So my name is In-Seok Hwang. I'm an assistant professor at Posttech Korea. And before joining Posttech, I used to be a research staff member at IBM Austin. IBM Research in Austin. And so in this session, this is the word cloud that I extracted from the 8 papers. So you can see various keywords pertaining to the sensing modalities, sensing technique, or some novel sensing applications or novel problems for, pertaining to sensing and so on. In this session, we have a total of 8 presentations, which consist of 5 IMWOT papers and 3 ISWC notes. So those are the 5 IMWOT papers. So you can see the list of the papers and also the photos of the presenters. And you know the drill. So for each IMWOT paper, you will be given 8 minutes to present your paper. And then maybe we can have a time, a very short time, to pick up a 1 or up to 2 questions. And then these are the 3 ISWC notes that would be presented in this session. So you can also see the presenters' faces. And each ISWC note will be given 4 minutes, followed by a very quick, short question. And then after that, as usual, all the presenters will be invited to the stage, and then we're gonna have about a panel discussion for 10 or 20 minutes. All right. So the first speaker is Fei Shang. Fei Shang is a second year of the PhD candidate in the University of Science and Technology of China, USTC. And his research interest is wireless sensing. Unfortunately, Fei was not able to come in person due to the visa issue. So instead, Fei provided a video presentation. So could you please the first video?
The introduction. Hello everyone, I'm Fei Shang. I'm here to share with you our recent work, PackquID, in packed liquid identification using F singles. This work has been done under my supervisor Panlong Yang and collaborated Yubo and Xiang-Yang. We are all from the University of Science and Technology of China. With the development of the IoT, UbiComp's material identification has received more and more attention. Many excellent systems based on communication devices have been proposed, such as TagScan, TagTag, VMin, Liquid ID, FG Liquid, and VI Liquid. However, they usually only consider the most ideal case. For example, there are no another atom between the various devices and the target. The target is placed standardly, and the liquid height is greater than the antenna height. Unfortunately, the actual scenario is often more complex. For example, when we put the drink in the backpack, the F-link is complex, because in addition to liquids, there may be another atoms in the packet, such as books. In addition, liquids and the placement of those atoms are often varied. To make matters worse, the height of the liquid is unknown. For such a less than ideal scenario, can we complex material identification? We have 3 goals. First, we want it to be able to identify liquids without being affected by other atoms. Then, we want the identification to be affected by placement. Finally, we want to be able to identify liquids that are not affected by liquid's height. The inspiration stream from that fact that when the waves are transmitted in liquid, the degree of attenuation varies with the type of liquid, which can be regarded as a unique feature of the liquid. However, there are several challenges that need to be addressed first. Since most backpacks are opaque, it is difficult to judge the area where the liquid is located. In addition, it is unclear how the impact of other items will be removed. In particular, the type number and the location of other items are unknown. Some previous work has shown that the received signal is affected by the heat of the liquid. That effect needs to be eliminated. However, neither the height of the liquid nor that of the antenna is unknown. Let's consider a basic case. A container with liquid is placed in F-link. The received signal strength is affected by 4 factors, including the attenuation in air, the refraction at the interface of different medias, the attenuation in liquid, and the gain of the receiving antenna. Different cause different attenuations, which we express in atom of alpha. It can be used as a feature of liquids. Similarly, other atoms can cause single attenuation. We use a calculation to express their impact. Many of the factors are similar for multiple receiving links. For example, the strength R0 depends only on the setting of the transmitting end. The transmission coefficient gamma is mainly related to the type of the media. The gain P depends on the antenna type. As a result, if we use 2 antennas of the same type to receive the signal, those factors will be similar, which means that we can use the ratio method to call them out. Now, let's think about how to tell if a liquid is in a packet. Let's first determine if the packet is empty. This is easy, because both liquids and other items can cause a large single attenuation. But how can we tell if those attenuation is caused by a liquid or something else? Fortunately, we found that the attenuation factor of source changes less with frequency than that of liquids. This means that when we test signals of different frequencies, liquid attenuation varies more large. In addition, these cross factors present an opportunity to eliminate the effect of other items. For 2 different frequencies, the attenuation factors of liquids are different, while that of other atoms are similar. Those allow us to use the ratio method to eliminate the impact of other atoms. We notice that the single strength is related to the head. The reason is that when the liquid level is lower than the antenna, part of waves retrieve the receiving antenna from the air, while another part is from the liquid. Let's remove the transmitting antenna so that part of the receiving antenna does not contain waves. The difference between them contains only liquid information. We model the electric field around the receiving antenna. Specifically, we express the transmission distance as a function of height. For a liquid, it is a 3-segment function. For an atom, it is a 2-segment function. Now, let's consider the difference in the segment of the receiving signal. It is the integral of an electric field over a small range. We found that there are many factors eliminated by the ratio method, and it can be solved with the previous method. Let's look at the result now. In our evolution setup, we use 2 USRP devices as well as transmitter and receiver. We use KN classifier for liquid identification. The accuracy expands 90%. In addition, we test the liquid with different height and placement. The average accuracy of identification expands 78%. Of course, there are limitations to what we can achieve. We can't tell components of an oil-based liquid, and the liquid with a metal container. This paper presents PackquID, which can use F single to identify liquid in the packet. It can cope with different atom and the liquid height. I'm looking forward to communicating with you. Thank you.
All right, so although the presentation was a pre-recorded video, the presenter, Fei, is in Zoom currently. So if you have any quick question, please come up to the microphone and then please ask a question. And then I believe that Fei should be able to answer your question.
This is more a comment than a question. There's a member of our community here, Ashutosh Dekne, who you need to talk to because you have overlapping interests.
Fei, were you able to hear Gregory?
Yes. Hello. Sir, could you repeat the question?
It was not actually a question, it was a comment. Do you know Ashutoshi? Maybe you can ask Gregory after the session is over. Okay, let's move on. So, Agrim, okay, please. All right, the second speaker is Agrim Gupta. He is a 50-year PhD student at University of California, San Diego. And his research interest includes low-power batteryless force sensors and sustainable communications. And here's one special remark. He's working towards commercializing his research on force sensors and would be open for collaborations and internships to help with this. Could you switch the video? Great. All right. The podium is yours.
Okay, perfect. Yeah, thank you, Professor Huang, for the introduction. I'm excited to present to you all 4 stickers, which are battery